So want to start with a quick overview of objective quality metrics, what they are, what they do. We'll talk a little bit about the tools and metrics that I use. We'll look at how to use tools like VMAF and SIM Plus to build your encoding ladder, and then how to evaluate other encoding options. I use, until about 5 or 6 years ago, everything I did was subjective quality comparison side by side. It got increasingly cumbersome as the files got bigger. You know, when you're working with 640 by 360 files, 8 years ago, you could put a couple of them in a Premiere Pro timeline and, you know, scroll through the file, look at the files comparatively. But when you start working with 1080p files and 3 or 4 different compression technologies or compression alternatives, it became increasingly difficult to do that. So I transitioned over to objective quality metrics probably 5 or 6 years ago, and I don't do any kind of analysis at this point that doesn't include getting the numbers. And as you'll see, I recommend looking beyond the numbers and looking at the actual frames and in some cases the video involved, but the numbers are a great way to highlight problem spots in the videos that you're going to be looking at. And you'll see a lot of that during this presentation. So what are objective quality metrics? They're mathematical formulas that attempt to predict how human eyes would rate the videos. So they're faster and less expensive than subjective trials, and they're automatable, which means you can build objective quality metrics into a quality control workflow. Some examples of objective quality metrics are peak signal to noise ratio, PSNR, SSIM, SIM Plus, which you'll see during this presentation, and VMAF, which you'll see a lot during this presentation. And I want to talk a little bit about the accuracy continuum. And we started over here with pure math, pure algorithm functions like mean square error and PSNR. And all they tried to do was come up with a number that represented the amount of difference between the compressed image and the source image. They didn't incorporate any perceptual values that relate to how a human being might perceive those differences. So if you had one encoding technology that removed film grain from a video, and another encoding technology that preserved the film grain but put little blocks in the frame, most humans would say the blocks look worse, but because these technologies don't take into account the perceived differences, they just quantify the math, they won't represent the fact that humans would see the blocks and think those were uglier. So those were the first two that we had, PSNR and mean square error. SSIM was very successful because it was the first metric that actually started incorporating how humans would perceive errors. So it was much more accurate than PSNR, and it's still in use today by companies like Facebook, the Moscow State University. When they put out quality comparisons, they use SIM as the metric behind their evaluations. And then as we move closer to the edge, on this side, we're seeing math plus perceptual plus machine learning. So that's VMAF. So what VMAF brings to the table is the ability to look at subjective ratings, build those back into the objective ratings, and get more accurate that way. So it's powered by machine learning. It gets smarter over time. And that's another aspect that neither SSIM or PSNR have. Those are fixed algorithms, never get smarter. You apply them, you know, they're the same today as they were 15 years ago. VMAF is going to get smarter. And SIM Plus incorporates all those three elements. They don't include formal machine learning, but they're continuing updating their algorithm via the engineers and the mathematicians that they have on staff here. Long story short, we started off with technologies like PSNR and SSIM that were still image-based. They're algorithms only, limited perceptual information, don't get any smarter. And we're moving towards technologies like SIM Plus and VMAF that were designed for video. So they know what an encoding ladder looks like, and they incorporate, you know, how things look when they're scaled, and they also incorporate how things look like when they're in motion, which the first, you know, PSNR and SSIM don't have any concept of motion in their algorithm. One of the 4 metrics that's in VMAF is particularly designed to evaluate the quality of the motion in the video. So we're seeing the algorithms get smarter, and that translates to more accuracy. Now this is a pretty dense slide. The metrics I'm going to talk about today are primarily going to be SIM Plus and VMAF. And the thing to understand about SimPlus is that the scores represent estimations of how a subjective viewer would rate the video. So if you see a SimPlus score of 80 to 100, that means they're predicting that a viewer would rate that score as excellent. And that's a very convenient system because at the end of the day, we don't care what a number is. We care what that translates to for how a subjective viewer would actually rate that video. And the other thing that's important with SimPlus is device ratings, because we know that video that looks good on a smartphone might not look good on a 4K television set. SimPlus gives you the ability to evaluate that and can produce a number for both devices, in fact, many devices. And the benefit of that is if you want to produce an encoding ladder specific to a specific set of players, you know, whether it's tablets or smartphones or 4K TVs or entertainment panels on airline flights, you can do that with SimPlus. Limited ability to do that in VMAF. There are three, well, I'll get to that in a second. One of the things I like about VMAF is that there's a study that you'll see later in the presentation that says if you get a VMAF score of 93, that either means the video looks perfect or it doesn't have any disturbing artifacts. Meaning, so if you get to a score of 93, that's pretty much what you shoot for. And if you encode at 2 megabits per second higher and you get to a score of 98, that tells you, well, this is a waste of bandwidth because once I get past 93, I'm really not improving quality perceptibly. And that's one of the key features of VMAF. It also represents scores pretty much the same way as we see with SimPlus, but it adds a factor called just noticeable difference. So you might, one video scores 81 for VMAF, another scores 82. Because it takes 6 VMAF points to make a just noticeable difference, you would say, well, nobody's going to see that difference. On the other hand, if one's 80 and one's 90, you're saying, OK, I know most people who view that are going to notice the difference between an 80 and 90 because 6 is the threshold. And we'll cover that a lot, or we'll look at that a lot in the presentation. And the other point, which I guess I forgot to circle, is that there are 3 device models for VMAF. There's phone model, 4K model, and default model, which is television set / 1080p model. So if I'm producing an encoding ladder for smartphones, I would use the phone model. If I'm creating an encoding ladder for 4K TVs, I would use the 4K. A couple of key concepts that I want you to understand because they're integral to what we do with video quality metrics. This is called a rate distortion curve. This is from a presentation I've got tomorrow afternoon that compares the transcoding quality of 4 real-time HEVC transcoders. NG codec is now Xilinx, Intel's SVT HEVC, and then X265 medium and X.265 very fast. And what this shows us is the VMAF rating over 4 different bit rates, all at 1080p video. So we're seeing here that SVT HEVC is the lowest overall quality through the 4 bit rates, and X.265 medium is the highest. So this is called a rate distortion curve, and pretty much any time you see anyone comparing technologies, you'll see a chart like this. And you can produce this fairly simply in Excel. You probably can do it in Google Sheets, but I never learned how to do it in Google Sheets. And the way to do that is to just create a chart. It's got to be a scatter chart, and then feed in your data. Now, the other thing you see when companies analyze codecs is what's called BD rate functions. And what we're seeing here are Facebook's when Facebook analyzed AV1, they compared it to X.264 main, X.264 high, and the VP9 codec. The VP9 is in gray. You see VP9 is in blue, high is in gray, and main is in brown. So these statistics, on average, show that AV1 produced the same quality as X.264 main profile at 50.3% lower data rate. So they're saying we can save 50% of the data rate with AV1 as compared to the main profile. You can save 46% as compared to the high profile, and you can save 32% as compared to VP9. So where did they get these numbers? How did they compute these numbers? Because again, along with rate distortion curves, these are the numbers that you see people quoting pretty much consistently. And these are called, I have no idea what they're called. I know the spelling, but I'm not quite sure about the pronunciation. I say something like Botnagard, but I'm not sure that's 100% correct. But we saw the rate distortion curve, and BD rate measures the average difference, the same quality between these two curves. So this is curve A, this is curve B. At the same quality level, this is obviously a higher quality. So at the same quality level, this measures the amount of savings. So when we looked at the 50% savings before a moment ago, that would say at 50% the data rate, you can deliver the same quality. And the BD PSNR shows you at the same bit rate how much better this technology is. So a lot of times when you see, pretty much any time you see companies compare codecs, you see the BD rate functions. Sometimes you see the BD PSNR as well. You can do those with any metric. Doesn't have to be PSNR despite the name. How do you compute these numbers? That's an article on my website, Streaming Learning Center. You can see the bit.ly URL there. And that explains how to do it and explains how to download an Excel spreadsheet that's got the macro in it that allow you to do those calculations. And it's pretty simple. It's explained better in the article than it is here. But again, this presentation is available for download now. If you didn't get here early enough to see the first slide, I'll go back to it at the end. But the article does a better job explaining how to do this than I could do in front of you. But it's pretty simple. Yeah, like I said, let me let the article do it. Okay, the tools I use or recommend. I use the Moscow State University Video Quality Comparison Tool very frequently. I use the SSIMWAVE VOD Monitor very frequently, and I use the Hybric, now Dolby Media Analyzer very, very frequently. The thing about Dolby is they've got a wonderful media analyzer tool, but it's a cloud encoding tool. And you can't just access the media analysis functions. You have to use the cloud encoder. And since they charge by the month, they've got a different kind of charge scheme. It's not, a lot of people can't use that. Unless you're using their system for encoding, you can't get to the media analyzer. So I'm not going to spend a lot of time on that. It's great for me because if I need to process 100 files or 1,000 files overnight, I can just upload them to the cloud. I can, let my AWS account spin up 100 machines, and I can process those files in a very short period of time. If I tried to do that on my workstation, I could probably do it in like 4 or 5 days. But again, that's not something you can access unless you're a Hybric customer. So the tools we'll spend our time on are the VQMT and the SSIMWAVE VOD Monitor. With the VQMT tool, what I do is I load the source file via drag and drop here, and then I can load 1 or 2 encoded files. And what we're showing here is the difference between constrained VBR and constant bit rate encoding. So I drag the source file here, the first process file here, that's constrained VBR. The second process file here, that's constant bit rate. And then I choose the metric. In this case, I'm using VMAF. And then I press start. And then it produces a results visualization it's really critical. We'll look at how I go through the analysis in a moment, but what this tells me is the average VMAF score or the per frame VMAF score over the duration of the file. And because I've got 2 files up here, the constrained VBR is in red, the constant bit rate is in green, and what I notice here is that there's a lot of downward spikes in the green file. So even though the scores are relatively similar, I can look at this chart and see, okay, there are some problem areas in the CBR file that probably represent visual quality differences that customers might notice. So the top graph shows the entire files. The bottom chart shows a highlighted region here. So if I dragged my mouse over this, it would show this region down here. So I can zero in on the frames that I want to, and then once I've zeroed in, I click this and I can see the actual frames. So I go from, a pure number to the ability to say, hey, there's a real difference here. This is a beta version of version 12, which is just out. And what they added in this version for people who haven't, people who have this product but haven't seen the newest version, is the ability to see the actual VMAF score for the frames when you're looking at it in this mode. So this tells me that the CBR file has a VMAF rating of 47, and the constrained VBR file over there has a VMAF rating of 69. So basically that tells me, yeah, even though the average value is about the same, there are serious issues in the CBR file that is going to degrade viewer satisfaction with that. And then here's the CSV file. You can get your output in either CSV or JSON. That's the source file. Those are the two files we saw analyzed. And this is kind of interesting. The VMAF mean, the mean score, we're seeing that CBR is higher. The harmonic mean, which takes into account the lower variability of the CBR score, we're seeing the VBR score is higher. And this is new for the Moscow State University tools. They put out they added the harmonic mean to reflect files that have a lot of problem areas. And then you can see the minimum value. That's really nice because that's a mathematical representation of the ugly frames we just saw. Maximum value, and then the location of those two files. And then the standard deviation, which again is very valuable because the higher the standard deviation, the higher the variability in the quality. So if you see it, you see right here that the VBR file has a standard deviation of 7, the CBR file 10, so there's a lot more quality variability in that file. And that's another useful gauge in terms of how many problem areas they may be in that file. And then the variance numbers is just the standard deviation squared. Okay, what do I like about the Moscow State tool? It's affordable, it's GUI and command line, it's very visual, you can see the results very easily. It handles most major algorithms except for SimPlus, and you can read my review of the technology at that bit.ly link. Can only compare files of like frame rate on the con side. So if I have a 60 frame per second source and a 30 frame per second output file, I can't get a quality rating for that file. You can do that with SimPlus. It's one of its key advantages. And then from my perspective, the other thing about Hybrid, in addition to processing a lot of files, is it lets me download one CSV file that I can just populate into a spreadsheet and I'm done. With Moscow State University tool, if I analyze 100 files, I've got to open up 100 CSV files and then copy and paste the results in. So I'm not smart enough to know how to use JSON to automate that kind of input, but if you're using CSV, it takes a long time to get the data in. So here's the SSIMWAVE VOD Monitor. It's based on the SimPlus algorithm, which is an advancement over, it's by the same people who invented the SSIM algorithm, so it's an advancement on that. We saw that it rates videos on a scale that corresponds with human perception. It's got multiple device ratings. It can compare different resolutions and different frame rates, and they're here at Streaming Media West if you're interested in the product. The other thing and we're going to see a demo of this, the other thing that the SimPlus VOD monitor can do is it can compute the BD rate functions that we learned a few minutes ago. So, with the Moscow State University tool, if I want to compute BD rate, or they call it SimPlus gain, I have to create these CSV files, enter them into Excel, apply the macro. With the SimPlus VOD monitor, they've got a comparison mode. In this case, we're looking at the difference between HEVC and H.264. So we've got two encoding ladders. This is the H.264 encoding ladder. This is the HEVC encoding ladder. We see that at every point across the data rate spectrum, the blue line for HEVC is higher. This number here tells us that if you use the HEVC ladder, you're going to save on average about 45%. So same quality at 45% lower data rate. And this is all, once all you do is select the files you want to analyze, and you can produce these numbers very quickly. It's a really good feature if you're doing a lot of codec analysis or a lot of encoder analysis. You know, I talked about Hybrid a couple times already. You can get some of these numbers through open source tools. You can compute VMAF with FFmpeg and VMAF Master. There's 2 articles on my website that give you the code you need to do it and tell you how to do it. The problem with using the open source tools is you get the numbers only. You don't get the ability to look at the files beneath the numbers. And I find that, you know, very, very critical. So, you know, this is kind of my pitch on how I use the technologies. I start with a number. I check the results plot. Then I check the actual frames. If there are problems in the actual frames, I'll check actual video. And this is kind of the project we looked at a few minutes ago. This is the VBR versus CBR. We saw the graph. What I would do after that, okay, I guess we're going to see a video here. So I'm dragging to see the region. I'm clicking the file. Now I'm showing the frame. And you can show the frames either side by side or one on top of the other, which is kind of the view I prefer. And then on the bottom left, I'm changing from the source file to the constrained VBR file, I'm sorry, to the CBR file to the constrained VBR file. So this is the Moscow State University tool. If I see there are problems in the original frames, I actually load the videos into a video editor, and this is side by side in Adobe Premiere Pro, and then I find the problem areas in the file that Moscow State or SimPlus identified, and then I create a video of those regions and play it back and forth to see if I can see a difference in the actual video. Because all we care about is, do viewers see the difference in the video? We don't care about the scores. We don't care about the frames. We care about, would they notice the difference? So if I'm going to look at 2 encoders, I'm going to use the SimPlus score, the VMAF score, as a way to, you know, come up with a bunch of numbers, but I'm going to look underneath the numbers to, you know, they also identify problem areas. I look at the problem areas, and I look at the problem areas in real time before I make a judgment as to which technology is better than others. If there's a 1-frame problem, viewers aren't going to see it. If it's a 3 or 4 frame problem, viewers are going to notice, and it's going to start to degrade their quality of experience. And I think
one of the more useful functions of objective quality metrics is in making informed configuration decisions when it comes to encoding your videos. And one of the most basic configuration options you have to decide is the bitrate control technique that you apply to your files. So here, we've got it set up to help us figure out whether constant bitrate is the better option or variable bitrate is the better option. And we've encoded 2 files, and the only difference between the encode, obviously, is one that has variable bitrate encoding, the other constant bitrate encoding. We see that the bitrate is very similar, obviously the same.
And this is the SSIMWAVE VOD Monitor.
And here is the score, the QoE score, as measured by the SimPlus VOD Monitor. And the scores are relatively similar. This is a 61.93 for the variable bitrate and 61.5 for the constant bitrate. And we're measuring this on a 65-inch television set. And down here is this score over the duration of the video. And what's interesting is we see, you know, green is the variable bitrate file, and blue is the constant bitrate file. And we see that for most regions of the 2 video files, the scores are relatively close. But there are times in the file where the quality drops significantly for the constant bitrate encoded file. And the obvious question is, well, what do those frames look like? And to see that, you would just click the frame. And here we see the constant bitrate file. Here we're comparing it with the original. And if we want to compare it with the variable bitrate file, we simply select that here. And now this is the constant, this is the variable, and we can view the whole frame. This is constant, this is variable. So we see that there's a pretty significant impact on quality, and that impact lasts for quite a few frames. The question is there a number that could tell us that this degradation exists? And with the SimPlus VOD Monitor, there is, and that's the weighted average index QoE score. And here we're seeing that the variable rate weighted average index is 55.9, or about 56, and the constant bit rate is 49, because this score incorporates the negative impact of the lower quality variations in the CBR file. If you wanted the score to even have a greater differential, you could do that fairly easily by coming up here and adjusting the default value to a lower value, say 5. And the score here is 56 versus 49. And here, by adjusting the value to 5, we're saying we want to incorporate more impact of lower quality regions like this in the comparative score. And here we see 51.6 to 39. And if you think that you're not so worried about lower quality regions, you can make this number higher. And here the differential drops from 6 to 4. And let me set it back.
Okay, so that's the cool thing about the SIMWAVE VOD monitor is you can actually use the weighted average index to, if you really want to avoid ugly video, you can pump that number down and you'll have a greater diversity in score if there are ugly regions in the frame. If you're not so concerned about that, you can increase the number and then you'll get lower variations relating to that.
Was that white curve the score of the source material?
Yes.
How is it picking that up if that was the reference? Like if it doesn't have anything to compare it to?
No, it does. This is a reference metric, and it's got when you load the file, you load the source file and the two distress files.
I'm just wondering, how is it scoring the source file?
It's their algorithm. Bart's here and he can. I don't want to take class time, but he's right there if you want to ask him or ask him at the booth. Okay, so a couple of ways that I use quality metrics in my practice, and one of the most important ways is finding the top rung. What's the maximum data rate you want to use for a file or a set of files? And I use a function called constant rate factor or CRF encoding. Who here knows about CRF encoding? So CRF encoding is, if you encode to a specific data rate, you tell FFmpeg or whatever your encoder is, you say encode this to 5 megabits per second, and it varies the quality up and down based upon the complexity of the file. If you tell FFmpeg or your encoding tool to encode using CRF, it produces the quality that you want. So the range is 1 to 51. Lower scores are higher quality. So if you encode it at CRF 23, then the data rate will vary over the duration of the file as the encoder produces a file that delivers CRF 23 quality. Now, we don't care about CRF 23, but as you'll see, from what I found is if you're encoding with X.264 and you use CRF 23, that roughly delivers VMAF quality of around 93 to 95, which basically means that, we saw a few minutes ago, at 93, your quality is good enough to ship. So if you want to figure out what the data rate is to deliver 93 VMAF scores, just encode it with CRF 23, and you get the result. So what I'm showing here is, I wrote a book about 4 or 5 years ago called Encoding by the Numbers. And what I tried to do in that book is I tried to, every configuration option that I could think of, I represented in a visual quality metric. Back then it was PSNR, now I'm transitioning that to VMAF. And the first thing I had to figure out was what data rate do I want to encode at? Because I didn't want to encode, I wanted to try a bunch of different files because I know different videos encode differently, but I didn't want to encode them all in the same ladder because, a configuration option that, this is a simple talking head video, and if I'm encoding that at 6 megabits per second, nothing I do from a configuration standpoint is going to make any difference. It's just too much data rate. The quality is always going to be good. So the way I figured out what data rate to use is what I just said, the CRF 23. So what we're seeing here is we've got 8 different files. We've got a Camtasia-based video. We've got a PowerPoint that's pretty much like this. It's PowerPoint with a small talking head video. And when I encoded that with CRF 23, I got a bit rate of 1 megabit per second. When I encoded my music video or DSLR movie-like production with CRF 23, I got 6 megabits per second. But if you look at the VMAF scores, they're all above 93 except for this one, and the average is 95.96 with a standard deviation of 1.39. That means very low variability, which means good predictability. If you want to know what data rate you need to to encode a file to produce 93 VMAF scores, which again is good enough quality, encode with CRF23. And here's the paper. You know, I've referred to this a few times. That's the paper and the bit.ly URL to that paper. And what was interesting from my perspective is, you know, CRF23 is a measure of complexity. How hard is the file to encode? It's going to vary the data rate to deliver that quality level. So I uploaded those files to YouTube, and I downloaded the top file that YouTube created, and we see that YouTube here and CRF23 follow a very similar pattern. So YouTube's per title encoding engine is based on, you know, probably millions of dollars worth of artificial intelligence and machine learning. CRF23 pretty much delivered the same pattern, and it's been in X.264 since it was invented. So this was kind of a nice reality check that says CRF23 is pretty much doing the same thing YouTube's doing. The data rate was around 1 megabit per second lower, and the VMAF points for the YouTube videos was about three VMAF points lower. So YouTube is putting out a little bit lower quality, but the pattern is very similar, which pretty much verifies that CRF23 is an accurate gauge of quality. And then once you have the highest bit rate, building your encoding ladder becomes very simple. You pick a low point, you pick the high point, and then you fill in the blanks by jumping between 150 or 200% apart. So this file, you know, 3.1 to 4.6 is around 150%, 2.1 to 3.1 is around 150%. Same thing, same thing. You don't want them too far apart because then you strand viewers. You don't want them too close together because then you change data rates for no real reason. And then the next question is what resolution? So we've got the data rates here. The next question is what resolution? And when this is a Netflix approach, what they do is they encode each file multiple times at different resolutions for each data rate. And then they take the highest VMAF quality file at each data rate point. So here we know what the data rate's supposed to be. And then we know we've got a 200 kilobit per second file, 600, 1 megabit per second, 1.6. And all I'm doing here is choosing the highest VMAF rating at that data rate among the resolutions that I encoded at. So this is a very brute force way of doing it. This is what Netflix does, or something similar to this, what they do for every file that they output. But they can do that because they want the absolute, you know, highest quality for the lowest bit rate, and they're getting millions and millions of viewers. I wouldn't do this for one file, you know, at my volumes, but I do this for OTT shops that have shows that are very similar. A lot of talk shows, a lot of game shows, a lot of sports shows. You would kind of do this for a per category encoding approach, not per title. And you know, just to get a sense of what an encoding ladder should look like for a specific segment of videos. And then if you're doing this for H.264 and HEVC, you just need to understand that you need to create a separate ladder for both technologies because HEVC is it's a more efficient codec, so you're going to push the switch point between 1080p and 720p much lower, because HEVC is going to be much more effective at higher resolutions. And you pretty much don't need the lower resolutions in the HEVC encoding ladder because, again, they're more effective at higher resolutions. At 200 kilobits per second, with H.264, we're still seeing files in the 360p range, and then we never got to 360p. They're higher quality at 432. Long story short, if you're encoding with VP9 or HEVC, you need a different encoding ladder than you need for H.264. And same deal for different types of content. You know, typically with animation, Syntel is much more, you know, there's some character generation in Tears of Steel, but Syntel is much more animated. Animated videos typically look better at higher resolutions, lower in the encoding ladder. So you want to do this analysis for different categories, particularly for synthetic type content. The other thing that I do quite frequently with these metrics is choosing the optimal encoding time quality trade-off. So this is the X.264 preset. The default preset is medium. A lot of people use that. That may or may not be the right preset to use. A lot of people go to very slow thinking, I just want the best quality. This analysis gives you a way to figure out what the trade-offs are between encoding quality and speed, which is what the preset does. And I use this technique when I'm comparing encoders, when I'm comparing codecs, and when I'm choosing encoding settings. So the test procedure is you choose your test files. You encode them to around 96 VMAF scores, and that's going to vary based upon the content. You measure encoding time, you measure VMAF, and then you measure low frame VMAF. So we saw the MSU tool puts out low frame ratings, and we'll see how we use those here. So this is the average VMAF score. We've got the separate presets, and we see ultra fast, super fast, very fast, all the way up here to placebo. A couple of points are really, really clear once you do this analysis. Number one, there's only a 6% difference between the average VMAF from the best to the worst. And the worst is red, best is green. So point one is there's not that huge a difference in terms of average quality. Point two is that placebo never give you the best quality. So placebo is off the table already because it never gives you the best quality. And then this is low frame VMAF. So what is the lowest frame output by these presets? And here we're seeing really scary scores. You know, what's the target for VMAF? It's 93. You know, here we're seeing average of 70, average of 68.52, and we're seeing a differential between the best and the worst of 33%. So that tells you that it's not average VMAF score you want to pay attention to, it's low frame score. So this is a graph of encoding time. The blue is average VMAF score. The red is low frame VMAF score. And what we see is that average VFrame score, you'd say, well, I could use the ultra fast and super fast, but if I look at low frame, I see that I really want to start at faster, because that's where the low frame quality stops being an issue. And then you see it, you know, at the medium preset, you've got 98.7% of the overall quality, and at 100%, at very slow, you've got 100%. So if you're using the medium preset, you could drop to the faster preset. You could almost double your throughput, and you're only going to drop from 98.7 to 96.4 VMAF quality. Less than a point, very few people would notice the difference. On the other hand, if you're one of these people who said, well, I'm going to use very slow because I want the best possible quality, if you go to any of these other ones, you can double, triple, or quadruple your throughput without any impact in quality. So, and then of course, I want to check the results plot. This is ultra fast. I can, you know, check those frames and see that there are ugly frames. If I go to faster, most of those go away. And so, you know, if I'm testing AV1 or I'm testing HEVC, I do this kind of analysis because I want to use the preset that most producers would use. It doesn't make sense for me to test H.264 using the placebo preset if nobody will use that because it's too expensive. So anytime you test a new encoder, a codec, you should do this kind of analysis to figure out what the average producer would, or what you think you would use it at, and then test it at those parameters. And we've got time for, we've got 2 more videos. You want to see H.264 versus HEVC or per title encoding? This is the SSIMWAVE VOD Monitor. Who wants to see HEVC? Who wants to see per title encoding? Per title encoding it is.
Not all videos are created equal. Some are hard to compress and some are easy to compress, which is the reason that a lot of video publishers are moving to per title technologies. Now, you can't really move to a per title technology unless you have a tool that can let you evaluate the differential between the fixed bitrate ladder and the per title encodes. And that's what we're going to look at here in the context of the SSIMWAVE VOD monitor. And we're going to be looking at the bit move and per title encoding function, which actually is a very high quality per title as per the measurements I've done in previous analyses for Streaming Media East and some others. So we're going to look at two test cases, a hard to encode clip and an easy to encode clip. So this is a football clip. It's relatively hard to encode, and this is our fixed bitrate ladder. And this is going to look identical in terms of data rate and resolution to the fixed bitrate ladder for the talking head clip. Here we see a maximum quality of 83.1, which is in the excellent range. The Simplus score 80 to 100 means it should be in the excellent range. But you're sending this to a 65-inch television set, and if you're a paid subscription service, you may want to deliver a higher quality experience to your premium viewers watching in living rooms. So here's the green is going to be the fixed bitrate ladder, and the blue in this case is going to be the per title ladder as produced by the bit move and per title encoding function. And we see here that the maximum data rate was boosted from 4.5 megabits per second to 5.4 megabits per second, and the score was boosted from 83 to 87. Now both are in the excellent range, but most viewers, particularly those watching on a 65-inch television set, are going to be able to tell the difference. So that's a hard to encode clip, and this is where you want to increase the data rate to reward viewers watching on high quality displays with high bandwidth retrieval capabilities. And this is the reverse case. This is a talking head clip. And again, the fixed bitrate ladder is going to look the same, except here, the 4.5 megabit per second, the top quality 1080p clip, is going to produce a SimPlus rating of around 90.3. And let's look at what the bit move and per title ladder looks like. Let me maximize that. And this is the blue again is the per title ladder as produced by BitMoven. Now note that this is an automatic function. Basically you upload the file in both cases and just tell the encoder apply the per title encoding functionality, and you're not doing anything else beyond uploading the file and selecting that function. Now here we're seeing that BitMoven reduced the bit rate from 4.5 megabits per second to 2.5 megabits per second, and the SimPlus score only dropped from 90.3 to 88.7. And for the 720p clip, the data rate dropped from 2.7 with a score of 87 to 1.6 to a score of 87. Or I guess it's 88.7, 87. And what we see here, the increase here between the blue ladder, which is the per title, and the green ladder, which is the fixed, means that all viewers watching in these data rates are going to get a higher quality experience with the per title ladder than with the fixed ladder. So you get the best of both worlds. You're saving bandwidth significantly on your top two rungs in your encoding ladder, and you're delivering a very, very equivalent experience. And here, you're increasing the bit rate. You're spending more, but you're delivering greater QoE to your people who are watching on a high quality device with high bandwidth retrieval capabilities. So again, what we're seeing here is the ability to gauge how effective a per title encoding technology is. And in this case, the SimPlus VOD monitor proves that the bit move and per title encoding technology is very, very functional. Again, best of both worlds. Increased quality of experience and data rate with hard to encode files, and reduced bandwidth with very little impact on quality for easy to encode files.
Okay, let me put this up. So you can download the presentation at this bit.ly URL. It's there now. And I just want to shameless plug here. Anybody who's interested in learning more about video quality metrics, I've got a course available, courses at streaminglearningcenter.com, that goes over pretty much everything we covered today and a whole lot more.
So the tools you're using to compare the quality of the source and the...
I'm sorry, could you start?
with the tools that you're using to compare the quality of the source and the compressed files, first question, do they deal with alignment, misalignment of those files? And second question, how do they deal with different frame rates and different resolutions?
Okay, so good question. The question is, how do the tools deal with alignment? And sometimes when you encode a file, you may drop a frame at the start or add a frame at the start, and if they're not aligned, then the scores are obviously, you're not measuring what you're hoping to measure because you're measuring different frames. So the SIM plus VOD monitor automatically aligns. The Moscow State University tool, you can manually align the files, and the next version is supposed to have automatic alignment. Now, in terms of resolution, both of the tools will scale up to the source resolution to compute it, so you don't have to do that. You used to have to do that with the Moscow State University tool until 11.2, meaning the version 11.2, but now they do that automatically. And then different frame rates, the SIM Plus tool can incorporate some different frame rates. It has to be 50%, like 60 or 30. It can't be 60 and 45. The Moscow State University tool can't. You know, you can come up with a number, but you know, what I do, never mind. This, the Moscow State University doesn't. SIM Plus does.
Do you mind showing the link again?
I'm sorry?
Do you mind showing the link?
Take down my product that I'm selling? Is that what you're saying? Any other questions?
Two kind of related. You said there's automatic frame alignment. Is there a max frame difference?
So is there a max frame difference for automatic alignment? Ask Bart. I don't know. I mean, I haven't run into that problem. I've never seen a file that it didn't align. But typically, it's unless you're doing something very wrong, it's typically going to be like 1 or 2 frames, and it seems to handle that automatically.
The question is because I think about live applications. If I capture a source and then I can broadcast output, there's a big difference there in aligning manually.
Okay, I mean, good point. Talk to Bart because they've got a live VOD monitor as well. It uses the same technology, but it works differently. We covered only VOD, and that's good point.
When you're hopping around from different tools like Adobe for doing your side-by-side and some of these other encode or analysis tools, like do you ever have to watch out for like whether the decode process is deterministic? Like for the same bit stream, would you get maybe a different frame decoded using a different tool, that kind of thing?
Good question. So do you sometimes get different frames? If sometimes you see that, and then if you with the Moscow State University tool, whenever I've seen that, the first few times I saw it, I would convert to YUV to just see, okay, is there a difference with those? And it really was more what you're saying. The analysis part worked fine. It just, when I was looking at the different frames, they could be different. If I change to YUV, that eliminates that problem. Okay, let's go. Oh, one more.
You made a comment earlier about temporal.
I'm sorry?
You made a comment earlier that some of them supported temporal quality.
Okay.
But you mentioned a lot of things you were looking at was like the minimum VMAF score per frame or such. How do temporal artifacts get captured in some of this other than just looking at
I'm sorry, how does what?
How do temporal artifacts get captured rather than just looking at the minimum VMAF per frame or something like that?
Okay, so how does VMAF capture temporal? I don't know. I know that they fuse 4 metrics, and one of them focuses on the temporal side, but I don't know.
Be able to assign that to the
Well, I mean, all I see is the score per frame, and that incorporates that, but that's all I know.
What would you recommend, or how would you recommend using the objective quality metrics with user-generated content?
With UGC? So how would I recommend using this with UGC? I mean, you know, interesting question, because Facebook, you know, they produced one of the analyses that we saw. They wanted to know, you know, which codec does a better job. So you have the source video with UGC, you're going to create encoded versions of that, so you would just use it like any other. I don't really see a difference. Okay, thank you very much. Thank you.